Okay, so we'll get started. So first, I want to let you know that your exam solutions are online. Okay, so because you guys are taking different exams, so I will not go through the solutions in class, but you can check on the solutions and compare to what you get, and also if you have any questions, you can let me know. Okay, so if you are taking the exams online. Some of the problems are from Wednesday's exam, but and then maybe a couple from Friday's exam. You can compare both, and then there's also some that is not from those two sets. Okay, let me know if you have questions on any of the ones you don't get solution to compare with. Okay. um, Also, homework for solution is up online. Okay, so that's the solutions to the exam and homework. So let me see. Okay, so for in-seat, Ryan and Alyssa, you guys will be doing the disinfecting today. Homework 5 still on Tuesday next week. Okay, and then 6 will be up online at some point next week, probably Tuesday, but it's still a week after next Tuesday. All right. And again, as I mentioned last time, for exam 2, this time we'll have the Friday group, in-seat group take exam first, which will be on Monday on the 12th of October, and then Wednesday we'll be taking it on Wednesday on the 14th. Okay. Um, so the next exam will cover, I think chapter 4, 5, and 6. I'm not sure. So we cover one and 1, 2, 3. Yes, 4, 5, 6. Right, and then homework 4, 5, 6. Okay. All right. For those of you guys are taking or doing lab today, you may want to bring your face shield because for the lab part, you guys will be working close to each other. So when you are doing that, it's your best interest to have face shield on, okay, to protect yourself. All right. So let's look at the lecture part. So last time we talked about friction force. So basically two kinds of friction force. So when two surfaces are in contact, if there's motion or intended motion, then there will be friction between the two surfaces. Okay. So if they have relative motion, then we call it kinetic friction. And then if they are not having relative motion, just intended relative motion, then it's called the friction force is called static friction. All right. For kinetic friction, it depends on the normal force that is between the two surfaces in contact, not dependent of the speed or the area of contact. Okay. So then kinetic friction, the magnitude is equal to a coefficient mu k, a constant number times n. All right. So that's called coefficient of kinetic friction. And it's the normal force in newtons. Yeah, should be in newtons as well. All right. For static friction, now it can vary from 0 to a maximum number. All right. So that maximum number can also be expressed in this equation of F sub S means static friction maximum equal to mu S times M again. Okay. And it's the normal force. Mu S is the coefficient of static friction now. Okay, so just keep in mind static friction has a range from 0 to the maximum value. So then that means you do not always use this equation to solve for your static friction. Okay, sometimes if it's not maximum, then you will use the other relationship from your free body diagram to figure that out. Okay. All right. So today we will talk about drag force. So I think we kind of started last time, but drag force. So previously when we talk about friction force, that's when you have two surfaces in contact. Okay, Now, drag force is when you have an object inside a fluid, and then it's moving. So then the fluid is exerting a force that is opposite to its motion. Okay, so then that's called a drag force. So again, the direction will be opposite to the motion of the object. Okay, and for the magnitude wise, we will take a look in the next slide. But when we talk about fluid, okay, so it includes both gas and liquid. Okay, so if you are driving your car, if your speed is relative high, when you extend your hand, you can feel the air, okay, flow through your fingers. So you can see that's a fluid. Okay, and then water or other kind of liquids, they are also fluid. Okay, all right. So for drag force, it's actually proportional to the speed square or velocity square. Okay, and then it's also proportional to the area that is exposed to the fluid um, in that direction where you are having relative motion. So if you are going that way, then that's your area of contact. Okay, so that's the area. Rho is the density of the fluid. So if you have denser fluid, then the drag force will be larger. Okay, C is the constant number called drag coefficient. All right. Now, if you rewrite, so because these are constant parameters, C rho, okay, and then area, if you have the body that is moving in certain direction, then area is fixed as well, okay. Then in that sense, the variable will be speed. So speed can be changing from small to larger. So then force will be also changing from small to larger, okay. So in that case, you can see if you rewrite all this together as another constant, okay, as called B, so including the 1/2 as well. Okay, so then drag force is just equal to the constant times v squared. So it's just proportional to the speed square. Okay, so the larger your speed is, the larger drag force will be. Okay, all right. So because of that, think some techniques people are using. So for example, for the swim shoot, so it basically, I think it reduces the contact area. Okay, so then you can bring down the drag force. Okay, because if it's very close to your body, then your contact area will be reduced. Okay, and then for the C constant, okay, so it depends on the shape of the object. So then it actually has different numbers. Okay, so some cars are designed to have very small the drag coefficient of C. So for example, the Toyota Camry or Honda Civic, okay, etc., has small one. Bicycle has a very large 1.9 actually. Okay, so yeah, so if you need drag constant, you can refer to this table. Okay, all right. And some animals are very smart. They can I don't think they know drag constant, but they can apply that to their daily life. So for like geese flying in V shape, so the first one will relative larger area exposed to the fluid. Okay, the next one then it's going here, so it has certain reduced area. Okay, so in that sense, they will experience smaller drag force. Okay, and then they kind of switch like which one take the lead, okay, afterwards. So they can do that. By doing that, they can reduce their drag force, okay, against the air. All right, so as we mentioned earlier, drag force is proportional to the speed square, right? So then if you have an object, if you release in a fluid, so for example, if you have say water or oil or whatever, a bucket of it, and then you drop a ball, okay? So then in that sense, you can see as the or maybe a balloon in the air. So in that case, you can see due to gravity, it will start to have certain speed, right? Velocity. So then the drag force will be increasing in that sense. So as the velocity increases, then the drag force increases. Okay, so this one will start with like relative small number or from 0 and then increasing gradually. This one is constant, right? But at certain moment when your velocity is big enough, then these two could be equal to each other. All right, when that happens, then the net force on the object here will be equal to 0. So then you will no longer oscillate, right? When this guy is bigger than that one, this object will oscillate. Okay, so you can see at certain point later, when the two forces are equal to each other, they will cancel out. Then oscillation will be 0. Then your velocity will not increase anymore. Okay, so that's when you have your terminal velocity. That is the highest velocity that you can possibly attempt. Okay, so if you go skydiving, it's the same scenario there. Your drag force initially is smaller than your weight, okay, and then when you reach your terminal velocity, then it's the same as your weight, then you have your highest velocity, okay. So let's take a look on the terminal velocity here. On the example here, it says if a person falling in an air the terminal velocity of the person falling in the air depends on the weight and the area of the person facing the fluid, okay. Find the terminal velocity of both in meters per second and kilometers per hour of the 80.0 kilogram skydiver falling in a pike, which means head first position with a surface area of 0.140 meters square, assuming the density of the air is 1.21 kilogram meters cube, and then a drag coefficient of approximately 0.70, okay? So you need to go a couple of slides back here for this formula, okay? When this is the drag force is equal to 1/2 0 a v square. So 0 and a are given in the problem. So if you are looking for v, then you need to know your drag force, okay? So when you reach your drag force, your terminal velocity, your drag force is equal to your weight, okay? So set this to mg, then you should be able to solve for v in that case, okay? Just in case you wonder about what will be the conversion between kilometers and meter and then hours and seconds. Okay, so 1,000 meters in 1 kilometer, 3,600 seconds in 1 hour. All right. Okay, so I think we are going to check at the solutions together here. So when the diver reaches the terminal velocity, then these two should cancel out. Okay, so then velocity no longer increases. So you want to set that those two up. Fd equals to the drag force equal to the mass times as a gravitational acceleration. All right, and then drag force you want to use that expression. So 1/2 c rho a v squared equals to mg. Okay, you're looking for v. You are going to move everything else but v to the other side of the equation. Okay, so v squared equals to get rid of 1/2, you multiply both sides by 2. All right, and then divide both sides by c rho a. Okay, c rho a there. So get rid of those. So it'll be mg over c times rho times a. Okay, take square root of it of both sides. So then you have v on the left hand side equal to the square root of the quantities there. Okay, so everything else is given here. You want to just plug in the numbers. So g is 9.8 divided by 0.70 times the rho 1.21 kg meters cube times the area 0.140 meters squared. Okay, so if you plug in everything right, it's going to be 115 meters per second. All right, and then you can convert it into kilometers per hour. Okay, so if you guys have done this conversion so many times, you might just figure out that from meters per second to kilometers per hour, you simply have to multiply by 3.6 if you know this. Okay, so 115 multiplied by 3.6 will give you 414 kilometers per hour. Okay, so basically from meters per second, 115 here. All right, the first thing you want to convert is from meters to kilometers. Okay, and then the second step you want to do convert seconds to hour. Okay, so you can see from here 1,000 here, 3,006. Okay, so if you cancel out those, this is 3.6. So basically, whatever you have in meters per second multiplied by 3.6 to give you kilometers per hour. Okay, so that's all. When I say if you just multiply by 3.6, will give you the right answer. Yes. Oh, no. Yeah, I forgot to write that down. Yes. So 2 is still there. Yeah. Thank you for pointing that out. Okay. Yeah. So then it's still 115 should be there. Okay. So then this is 414 in kilometers per hour. All right. So You can see if your weight is less than 80, then you probably get a smaller terminal velocity. Okay, so it's proportional to your weight to the square root of it. Okay. Any other questions you guys might have? So I think I did see correct answers here a moment earlier. Yeah. So a few of you guys got this one right. Okay. Put this up again. All right. So this equation we just used the 1/2 0 AV square. Okay, this applies to relative larger objects. Okay, so like in our human body kind of size. Okay, or like a car, bicycle, etc. When we go to smaller scale, for example, like bacteria, very small objects. Okay, then the drag force, actually the formula changes a little bit. Okay, so in this time it's equal to, or it's actually governed by Stokes law. It's given as 6 pi. Pi is the constant of 3.14, and then this guy looks like m, but it's pronounced as eta. It's the fluid viscosity. So the fluid has different viscosity, right? Like thick or thin. For example, like water and honey. So honey will be having larger viscosity. So then eta for honey will be larger than water. Okay. And then R is the size of the radius of the object. Okay. So when we treat small object, we kind of treat them as just a sphere. Okay. So then that's the R, the radius of it, and then the velocity. Okay. So in this case, you can see it's just proportional to the velocity, not the square of it. Okay. So this is drag force for small objects moving in a denser media such as water. Okay. All right. I think so. That's the section on drag force. So move on to the next section here in this chapter on elastic. Okay. So for materials, this almost apply to any materials. Okay. So if you pull it, it's going to be stretched a little bit. Um, And then, so it depends on material. Some material you can see it immediately, like rubber, you can just pull it and then you can see that. But some material, it's not so obvious. For example, like metal, when you stretch it, it actually does change the length a little bit, but not noticeable. Okay, so um, then whenever you apply a force to a material, actually the shape will change slightly. So for example, the length will change slightly. So this is called deformation of the material. Okay. And elasticity is the measure of deformation of the object when a force is applied. Okay, so you can apply tension and then see how much length that's changed here if this is one-dimensional deformation. Or you can compress the material and then see how much length is being changed in that sense. Okay, so for small deformations, if the deformation is small and then the materials is uniform, so this change in length is proportional to the force you apply. Okay. So as I mentioned, for different materials, deformation is to different extents. So for like rubbers, nylons, and then steels, streams, they deform by different lengths, even though the same force is applied. Okay, so in this case, the same weight is applied, then you'll see different deformation. Okay, amount of deformation. So how much that deformation that is given in this equation, so the change in length, is proportional to the force, okay? Now it's inversely proportional to the cross-sectional area. You can see if you have a thin material, then it's going to be deformed more. If you have a thicker material, if it's thicker, then the deformation is less, okay? It's also proportional to its original length, okay? If original length is longer, then this delta L is larger, okay? Absolute value is larger. And then this Y factor here, down here, it's inversely proportional to this guy. Why? This is called the elastic modular of the materials, or the Young's modulus of the material. So that is the materials dependence factor. So for different materials, you can have different Young's modular or elastic modulus. So sometimes in engineering field, people measure this value. Okay, so they can apply force. This is something they can measure. They can measure the original length. They can measure the cross-sectional area. They can measure the deformation form under the force applied. In that case, so if you apply several different forces, then you have several different delta L. Okay, so as we learned in the previous labs, you can actually do that. So then you have a set of data of having different data points. You can plot it. Okay, so then the slope will give you information about this. So it's 1 over y times a, and then times L naught. Okay, so in that sense, you can calculate what's your y Young's modular to determine the material. Okay. So if we rewrite the equation, okay, we move the force and area to one side of equation and then the rest to the other side of equation, then you can see on the right hand side here. So this is from just from rewriting the previous equation. Okay, you guys can compare the original one and then see how that's done. But basically, this is what you get if you put F and A on the right hand side. So F divided by A, that's defined as stress. Okay, or actually that's also the definition for pressure. Okay, so pressure is defined as force divided by area. I think sometimes people use these two terms interchangeable, pressure and stress. Okay, but that's fine. It's the same as pressure. We'll check later on this semester. All right, and then on the other side, delta L over L, that's called the strain. Okay, so that's basically the deformation of material percentage wise. Okay, and then you can see stretch then is proportional to the strain. Okay, with the Young's modular as the multiplier before the strain. Okay, so that was one-dimensional deformation. You are applying force in one dimension. Okay, now sometimes you can apply force sideways to the object. Okay, so in this way. Okay, so then the area here perpendicular to this direction of the force is applied will have deformation. Okay, so that's two-dimensional deformation. All right. And then also the deformation is proportional to the force. Okay. You can have the three-dimensional or called the bulk modulus of the material. So that means if you apply the force in three-dimensional, then the material, its volume is going to be changed, okay, due to the application of the force. Okay, so that's called bulk modulus. And then this is called the sideways stress is called shear modulus. Okay. So if you guys encounter those terms, you know what do they mean? Or you can look them up here. Okay. So when you apply force, if your apply force is not so large, okay, so then you'll see deformation is proportional to the force applied. Okay. So and then this is linear proportional. And on this side, this is not so linear proportional. Okay, so if it's linear proportional, we call it Hooke's law there. Okay, and then if you are cover the range from here to here, it's called elastic region. That means you can apply the force after you release your force, the material can go back to its original shape or length. Okay, but if you go beyond that range, all right, then the deformation is going to be permanent. Okay, it will not return to its original shape or length. Okay, so then, but if you keep applying the force, at some point the material is going to break. Okay, so then it will have fracture over there. All right. The tensile strength is referring to the breaking stress that will cause the permanent deformation of fracture of the material. Okay, so when that's applied. All right, so I think these are just a few terminologies here. The only thing we'll care about is in this class, particularly is the Hooke's law. When you apply the force that is not so big to permanently deform the material or break it. Okay, so then force is proportional. Force applied is proportional to the deformation. Okay, linear proportional to it. So equals to K times delta L. Okay. In that case, you can see K, if you look at the original deformation equation here, you can see K is equal to Young's modular times area and divide by the original length, okay? But Hooke's law is our primary interest here because in this class, you may see a lot of times that spring is applied in a material. So then for the spring, it actually applies Hooke's law, okay? Unless otherwise specified, you're assuming that Hooke's law applies to the spring, okay? All right, so if you have a spring, then instead of writing delta L, we are going to use X as the deformation of the spring from its natural length. Okay, so if this is the natural length, then if you apply a weight here, so the force applied here should be equal to K times the X. Okay, and then if you apply twice of that, then there should be twice of X. Okay, so K is equal to, or F is equal to KX, and then K is called the spring constant. Okay, or sometimes it's called also force constant of the spring. So either way, all right. And then the direction of the force applied by the spring should be opposite to the direction of the deformation. If you pull the string, then the force is going to be pulling back against it, okay? If you compress the spring, then the force is going to be pushing backward, okay? All right. So on that we'll take a look one example here. Okay, so this one is combination of the spring force and then also the static friction here, okay? So you can assume here, so you are pushing against this spring and then spring is pushing against this block, which is in contact with the wall behind it. So the free body diagram, I think is indicated here on the block here. So there's force by the spring, there's normal force by the wall to the block, there's the weight of itself, and then there's this static friction force, okay? So 4 forces here to consider. It tells you the spring constant or force constant of the spring, all right, and then it tells you the mass of the block. It tells you the coefficient of the static friction, okay, which gives you the maximum force here, all right. Now it's asking you what will be the maximum compression of the spring, so the maximum X, all right. So I think I'm going to give you guys a few minutes to try to see if you can solve for this one or come up with a plan, and then we'll take a look on it together, okay? All right, so let's take a look here together. So this is the free body diagram. Okay, 4 forces, 2 in x and then 2 in y direction. So as we usually have been doing here, so we'll take a look at the free body diagram. You can write the net force in x direction. That's going to be equal to the force minus the normal force, okay, in this case. Because F is in the positive x, normal force is in the negative x. Then net force in the y direction is going to be the friction force, static friction force minus this mg. Okay. Now, from Newton's second law, so if you are holding this block stationary over here, that means the acceleration is going to be 0. So from second law, you'll tell you net force is equal to 0 in x direction, also in y direction. Okay. Now, I think we have been doing this types of analysis so many times. So in the future, you may just come up with directly like writing out this like this, okay? So x force in x direction from the free body diagram is equal to force times normal force, okay? The spring force minus normal force, and then write that directly equal to 0 because you are going to set that equal to 0, okay? So if you guys are so familiar with the such type of problem now, you can just write that out, okay? But if you are not, you can still do as what we did earlier. So write out the two equations from the free body diagram and then from the second law, okay? Also, in the y direction, you'll be doing the friction force minus the weight that goes to 0 because it's stationary, okay? Then you have these two equations. Now, in addition to these two equations, you will also have these two, or one equation here and then one um, um, not so-called equation, but relationship like this here, okay? So F is from the spring force equal to the spring constant or force constant times the X, which is the deformation of it. In this case, refers to the compression of the spring. And then friction force should have a range, okay? It has the minimum of 0 and then maximum of mu s times n, okay? So you can see now this is what you have. You are looking for this guy, right? So you probably can start from here. You can say, okay, I'm looking for X. Okay, so this is what you're looking for, X, and which says minimum. Okay, we'll talk about that minimum maybe later, but X is what you are looking for. Okay, so then you can come here, you look at all the equation you have, you can see, okay, this is my X in this equation. So X is going to be equal to F divided by K, right? I know K, but I don't know F. All right, so then we are looking for F. And then you look at those equations again, you can see, okay, I'm probably going to use that one to find my F, right? So then F equals to M from here. All right, but do we know M here? It looks like not, right? We don't know M here, okay? Now the question is, what's M? Okay, so the question was, initially was what's x, then we kind of looking at the equation we have, we say, okay, then it's equivalent to look for what's f. Now here, because f is related to n, so then it's equivalent to what's n, okay? So we have checked on this equation, we couldn't figure n, right? Then we can check on the rest of the information here. So it looks like n is in this relationship, right? So then you can write f as less or equal to mu s times n, but n is what you are interested, right? So you can say, so then n, so if you divide both sides by mu s here, okay? So then n is greater or equal to fs over mu s, right? Because fs divided by mu s is less or equal to n, so then n is greater or equal to that guy, okay? All right. Now, for the friction force here, right? Now the question, this one is given, now the question is, what's this friction force, right? So now it's this one remaining, right? This equation remaining. So that guy is equal to mg. So this is equal to mg over mu s, right? So originally we are looking for x, which is equal to f over k, and then f is equal to n, so it's n over k, right? So then that means x is equal to n over k, but n is greater or equal to that guy, right? N is greater or equal to mg over mu s. All right, so then x is greater or equal to mg over mu s, right? On the top, this is m divided by k, right? So you kind of doing like step by step, okay? So if you're looking for x, then check on what you have and then see you'll figure out, okay, then n is what you need, and then n is not given, so then to figure out n what's need next, okay? So kind of in that cycle there. All right, so then at this point, we kind of have concluded that x is greater or equal to mg over mu s times k, right? So that does tell us that x has a minimum, right? Because it's greater or equal to that. So if you set the equal, then that gives you the minimum, right? That's all we are looking for here. So then that tells you the x minimum is equal to mg over mu s times k, okay? So at this point, you can plug in the numbers. You are given all this information you needed, okay? So 0.27 kilogram times 9.8 meters per second square over 0.46 times 120, okay? And then that will give you 0.048 meters for your minimum, okay? All right, yeah, just checking on if we are missing anything else, okay? So this is how you find your minimum, okay? So I think maybe it's the first time you are looking at such a problem, but you can go through the solutions, okay? It should be you should be able to understand the logic here. So again, list what you have, okay? So from free body diagram and second law, from there you'll have two equations, okay? You'll have two equations here, all right? Now, in addition to these two equations, you also have these two relationship over here. So the spring force is given as K times X, and then friction force is falling in this range, okay? So because we are looking for X, so then you start with this guy. So in order to look for X, you need to know F, okay? But F is not directly given, so you turn to this equation, which has F in it, you'll figure out F is going to be equal to M. Again, n is not given, so then you'll check on the rest of two equations or two relationship here. You go find the n as in relationship with this guy here, but this guy again is not given, so we look at this equation. Okay, so kind of follow the dominoes there, like one by one piece. Okay, so at the end you'll be able to solve for the minimum compression there. Okay, any questions you guys might have? Okay. All right, so if not, we'll stop here for today. All right, and then see some of you guys this afternoon for the lab, and then rest of you guys on Monday.